Hello, this is an example illustrating the use of the LRFD load combinations in the ASCE 7 standard for a column in a typical building. In this problem, we're going to consider a column in a building that's subjected to a dead load of 80 kips, a live load of 100 kips, a roof live load of 20 kips, a snow load of 30 kips, and a wind load of 25 kips. All of the loads cause compression in the column except for the wind load, which can cause either compression or tension. The objective of this problem is to first determine the maximum and minimum factored loads that must be considered for design, and then, assuming that we have a resistance factor of 0.85 used to compute the design strength of the column, we want to determine the nominal strength that's required, R sub n. We'll start off by considering the load combinations shown here from the 2016 edition of the ASCE 7 standard. Like our previous examples, we'll define a roof loading that is considered to be the maximum of the roof live load, the snow load, and the rain load. In this case, the roof loading will be taken as the larger of the 20 kip roof live load and the 30 kip snow load, or 30 kips. This slide shows all of the possible permutations of the 7 ASCE 7 load combinations, but you can see that many of these permutations won't apply to this problem. We can eliminate all but 6 of the permutations that are shown here when we consider the loads that are given for this particular situation. When we substitute the magnitudes of our loads into these load combinations, you can see that the maximum force effect comes from load combination number 2, and that the minimum effect comes from load combination number 5. Note that when we evaluate load combination number 5 for the case where wind causes an uplift, that we substitute a value of positive 25 into the combination instead of negative 25. That's because there's already a negative sign built into the combination that addresses the idea that the wind acts in the opposite direction of the dead load. Now that we know that our required strength, the sum of gamma times Q, is 271 kips, we can divide by the resistance factor of 0.85 to determine the required nominal strength, which ends up being 319 kips. Finally, just as a check, here are the results of a spreadsheet that I've constructed to evaluate all of the possible permutations of load combinations 1 through 5. As a follow-up, let's consider a slightly different version of the same problem. In this version, let's consider that the live load in the column now causes 40 kips acting in tension, with the other loads remaining unchanged. When we substitute into our load combinations in this case, note that where the live load appears in a combination, that we have to substitute in a value of negative 40 kips. In this case, the implied sign convention is that compression is positive. Thus, with a live load that causes tension, we have to use a negative sign to indicate that the live load force is in the opposite sense of the other forces. Note that this is handled a little bit differently than it is for the wind load. Load combinations are built around the idea that the wind could be acting in either direction and, in the context of this problem, cause either tension or compression. Thus, there's a plus and a minus sign that's built into combinations with respect to wind. However, the same isn't true for the gravity loads. For gravity loads, we have to use the appropriate sign on the magnitudes of those loads as we enter them into the load combinations. Now that we have our new required design strength of 156 kips, we can determine our required nominal strength by dividing by the resistance factor of 0.85. In this case, you can see that we would need to have a nominal strength R sub n of 184 kips. Once again, here's a spreadsheet that I used to evaluate all the possible permutations of the first 5 load combinations just to check the work that I presented in the previous slide.